Okay, so it's great to be here. This is a wonderfully diverse conference in all senses of the term. So I'm going to be representing number theory here. It's completely different from most other talks, actually, in this conference. And so there's been a lot of recent progress in some very classical problems in number theory, and that's what I'm going to talk about, particularly involving gaps between the prime numbers. So you all know what the prime numbers are, of course, 2, 3, 5, 7, 11, and so forth. Yeah, okay. So some of the oldest questions in number theory concern the gaps between prime numbers. So if you call Pn the nth prime number, you can look at the prime gaps between consecutive prime numbers. So the first prime gap is 3 minus 2, which is 1, and then 5 minus 3, which is 2, and so forth. And so these are all the first few prime gaps. So they're just this sort of random-looking sequence. And two of the very oldest questions in number theory very roughly, basically, as you keep going along the sequence, how small can the prime gaps be, and how large can the prime gaps be? Right, so that's sort of those are sort of imprecise questions, but these are two very basic questions. And what's exciting is in the last few years, there's been breakthroughs on both of these basic questions after many years of being stuck, basically. And actually, the weirdest thing is that actually progress on the small gap problem has led to progress on the large gap problem, which is not intuitive at all, but I'll try to explain how that happened. Okay, so let's have small gaps. Let's have small gaps first. So, of course, the first thing you observe when you look at the sequence is that all the gaps are even, apart from the first one. And that's because all the primes are odd, apart from the first one. Okay, so that's not so difficult. So the prime gaps after the first one, they have to be at least 2. And one of the oldest questions in number theory, dating back at least to de Polymath in the 19th century, some people say that you could consider this, but there's no actual record of this. So the prime gaps have to be at least 2, and it's believed, and this is called the twin prime conjecture, that in fact that the prime gap 2 actually occurs infinitely often, that there are infinitely many pairs of primes that are distance 2 apart. So of course there's many of them, 3 and 5, 11 and 13, and so forth, but we don't know if they're gone forever. We know the primes go on forever, but we don't know whether the twin primes go on forever. So we can't solve this, even after all this progress. And actually there are good reasons for why we can't. There's a very solid obstruction to all of our methods for proving the twin prime conjecture. Something called the parity problem, which unfortunately I won't have time to talk about in this talk. But even though we can't solve this conjecture, we've been making progress towards this conjecture in many different ways. And one way to make progress on the twin prime conjecture is to show that while we can't show that the prime gap is 2 infinitely often, we can at least get upper bounds on the prime gap, which hopefully get closer and closer to 2, even if we can't reach 2 yet. So we have all these partial results. So the first thing you can do is you can use the most basic theorem in number theory, which is the prime number theorem. So here's what we do. Okay, so let's have a look at a big interval of primes. So let's pick a large number x, you can say 1 trillion, and look at all the primes inside, say, the interval between x and 2x. You could pick other intervals if you like, but let's just take x and 2x. And then you look at all the prime gaps inside this big interval. So you look at adjacent primes in this big interval, and you look at these prime gaps. Now, the prime number theorem is one of the most basic theorems in number theory. It tells you how many primes there are in a big interval. So one thing it tells you is that if you look at it at a big interval x to 2x, the number of primes in a big interval like that is roughly x over log x. So about 1 in log x of all the numbers in this interval are prime, up to an error which goes to 0 as x goes to infinity. So there's always little over ones here, which you should basically ignore for this talk. But basically, the number of primes in this interval is about x over log x. So the number of prime gaps in this interval is also about x over log x. And the interval is length x. So just from the pigeonhole principle, this tells you that one of the gaps has to be small. So you just divide the length of the interval by the number of prime gaps you have. And so the pigeonhole principle tells you that one of the gaps has to be at least log x. So at most log x, because that's just the ratio between the length of the interval and the number of primes. So just without any effort, really, apart from the prime number theorem, you can say that you can at least get a gap which is of size log x. Okay, but you want to get 2, right? And log x is bigger than 2 for big X. So, okay, so people have tried to improve this over the years. So it actually was remarkably hard. So this is a very easy bound, but to improve it took a long time. And the first few bounds were not all that terribly impressive, although very impressive mathematicians worked on them. The first few results basically improved that 1 times log x to a constant times log x. So for example, Hardy and Littlewood in 1926 worked quite hard using, in fact, a very powerful additional hypothesis, the generalized Riemann hypothesis. And all they could do, even after all this work, was to improve this 1 log x prime gap to 2/3 log x. And then this got slowly improved over the years. So Rankin a bit later got 3/5 log x, but they still needed the Riemann hypothesis, the generalized Riemann hypothesis. And then Erdős had a breakthrough in which he didn't need the Riemann hypothesis, but then he could only improve 1 by a tiny c, which he didn't even say what it was. They can get almost the smallest possible improvement to the result. And then that number slowly got, so then Ricci was the first to actually give explicit improvement to 1 to 15/16, and then it got slowly improved over the years. But as you can see, progress was not incredibly fast. But then in the last 10 years in particular, there was a lot of breakthroughs. So until like 2004, the only improvement was to improve the constant, which in analytic number theory is not terribly impressive as far as improvements go. But then there was a big breakthrough in 2005, by Goldson, Pintz, and Theorem, who showed for the first time that you can get prime gaps that are actually which grow at a rate smaller than log x. So log x times something that goes to 0 as x goes to infinity. So another way of saying it is that this constant that was steadily shrinking in the previous slide can be made as small as you wish. Then they worked a bit harder and said, actually, it's not just log x. You can actually get basically square root log x times an additional small factor after a few more years of work. And then this got improved a little bit to the cube root of log x. And then finally, in a quite famous breakthrough, actually, Yitang Zhang, who was actually just a lecturer at University of New Hampshire at the time, stunned basically the community who had thought that basically you couldn't do this, actually, with the methods we had, but found quite an ingenious argument that managed for the first time to get a bounded gap. So Yitang Zhang, what he showed was that there were infinitely many prime gaps, which aren't 2. That's what we would love to have. But you can get infinitely many prime gaps that are bounded, and the bound he got was 70 million. So that there's infinitely many prime gaps which are bounded by 70 million. Okay, so that was a big breakthrough. Almost as soon as this paper came out, so that paper came out 21st of May, or 2 years ago, people looked at this paper, and so 70 million was just something that came out of his calculations, and he was rounding up at all various places. He said in his paper that this was not the best result you could get. This was just sort of the cleanest number that he was going to write down. And so almost immediately people started improving it. So you can see on the archive, for example, the paper saying I can improve 70 million to 62 million, to 58 million, whatever. And so so on blogs and various over on the internet, various websites, people just started tinkering away at this bound because there was it was a very cheap way to get, at least very temporarily, the world record on a major mathematical result. And so this eventually got coalesced into a single project, what we now call a Polymath project. So Polymath projects were started by Tim Gowers, who's a mathematician at Cambridge, about 10 years ago now. And the idea of a Polymath project is that unlike traditional math research in pure math, which is usually 1 or 2 people working in isolation, and not sharing what they've done until they've almost finished, and then they release their preprints. A Polymath project, Polymath is just a pun, it just means many mathematicians. Okay. A Polymath project is where you have many mathematicians collaborate over the internet in an open environment. Anyone can sign up and comment, basically, usually on blogs. We also use wikis and Dropbox and things like that. And you just work on a common goal, which in this case was to improve this number, make it as small as possible. And people just toss out ideas. Other people try to carry them further. Maybe someone wants a calculation done. Someone else has a big computer and is good at programming and actually does the calculation, and so forth. And everything's done sort of openly. So people make mistakes, they backtrack, and so forth. And so there was this very chaotic process. I was actually one of the moderators for this project, which took basically a whole year of my life actually to deal with. But within a few months, we had managed to optimize pretty much every single step in Yitang's argument and squeeze this number down to 4,000 or so, which we were very, very happy with. And we were writing this up and about to publish it when we got another surprise because there was another mathematician, a young postdoc then at Montreal, James Maynard, who was working independently of us. So we were about 20 people, all working on different parts of Zhang's paper. Maynard found a different argument, simplifying a lot of what Yitang did, actually bypassing some of the most difficult parts of Yitang's argument, and getting a much better bound, actually. So he leapfrogged our bound to 600. But then what happened was that we decided to combine forces. Maynard joined our Polymath project, and we combined all our tricks, and we eventually got our bound down to 246, which is the current world record. And we're out of tricks at this point. To get any further, it's going to need something new. But this is probably not where that's not where that's not the best possible result. It's just the best possible result we can get with the tools we have. Okay, so that's a brief history of progress. Now, so this is just it's not a very good resolution slide, but so this is just an illustration of how fast the bounds were progressing at one point. So the Polymath project had this wiki page, and one of the most popular pages on this wiki was this timeline where we would describe what the bound was doing at any given point. So Zhang proved 70,000 as the bound for the prime gap back in May, and then this bound was dropping on a daily basis at various points. So people would wake up in the morning and just check what the bound was that day. It's like a stock market or something. It was well, maybe not like stock market. It was always going down. Yeah, so it was a fun. It's not often you get to see math sort of done in real time like this. So that was that was fun. But I'm kind of glad it's over because it was really quite time consuming. Okay, so let me kind of explain how we prove theorems like this. So so the first breakthrough, after the first breakthrough by Goldstone, Pintz, and Theorem, we all use what's called the Goldstone, Pintz, Theorem method, and we've just become very, very good at it. So to explain how this method works, let me go back to the trivial bound of 1 times log x. So this is the pigeonhole principle argument that I gave at the beginning, and let me prove it in a different way. And the purpose of doing this is to motivate the more advanced way of proving prime gaps. So okay, so let me reprove the bound that you can get a prime gap within the interval x to 2x of size bounded by log x. So you can prove this by sort of a probabilistic method. What you do is that you pick any number at random, any integer at random from this interval x to 2x. You just pick a number at random from, say, 1 trillion to 2 trillion. So this number will probably not be prime. But the prime number theorem tells you how likely it is to be prime. And so one way to think about the prime number theorem is as a probabilistic statement that if you pick a random number from x to 2x, then this number n will be prime with probability about 1 in log x. About 1 in log x of the time will be prime, which is not very much, but it's positive. And then if you add 1 to it, n plus 1, that's also pretty much another random number between x and 2x, maybe shifted by 1. So that guy will also be prime with probability about 1 in log x. And n plus 2 will be prime with probably 1 in log x and so forth. So if you add, so each of these probabilities is individually very small, but they start adding up. And so if you add up k of them, and if k is just a little bit bigger than log x, if you add up k of these events together, so each of these numbers, n plus 1, n plus k, up to n plus k, each of them are only prime with very small probability, 1 in log x. But if you put them all together, the sum of all the probabilities that these guys are prime will eventually add up to more than 1. And the moment that happens, then the pigeonhole principle for probability tells you that there must be somewhere in your event space where 2 of these guys are prime together simultaneously. And then that will give you a prime gap which is smaller than k, which is log x. Okay, so that's just a repackaging of the pigeonhole principle argument in a probabilistic language. Okay, so the idea of Goldstone, Pintz, and Theorem, which is so obvious in retrospect, but people missed it for 70 years, was that you run this argument where you don't pick n uniformly at random, but you pick it non-uniformly at random. You pick a biased n. So the modern way to find prime gaps is that you pick a number n using some bias distribution from x to 2x, and the whole art is choosing the right bias distribution. Okay, but you choose a clever distribution, a probability distribution on x to 2x, and you pick n using this well-chosen distribution, and you want to choose it in such a way that that various shifts of n, like maybe not n plus 1, n plus 2, n plus 3, but maybe n plus h1, n plus h2, and you have to pick the h1 and h2, but let me not talk about these shifts, but if, you pick some shifts h1 to h2 up to hk, and you try to choose your probability distribution so that each of these shifts has a large chance of being prime. So better than 1 over log x, something like, say, 1 over 100 would be great. And then if you can, all you have to do is that you need to make these probabilities of that each of these numbers is prime. If you can make them add up to more than 1, then again, the divisional principle will tell you that somewhere in your event space, 2 of these guys are prime at the same time. And that will give you a gap which is bounded by the diameter of this set of shifts. And so, yeah, so part of this, these 70 million numbers and so forth that come from trying to find good sets of k-tuples with small diameter, but let me not talk about that part of the project. Okay, so it's basically the same argument as the Pintz argument, but the main trick is to find a clever non-uniform distribution in which you enhance the probability that each of these guys is prime. And so what you want to do is you want to somehow remove or sieve out all the numbers where these guys are composite, or at least sieve out a lot of them, so that you keep the primes and maybe a few non-primes, but you try to remove as many composites as you can from your probability space. And so there's a whole area of number theory which is devoted to doing exactly that, called sieve theory. And so you have to choose a good probability density function so you basically want a probability distribution on your numbers, set of numbers n, such that each of these shifts, n plus h1, n plus h2, and so forth, you want them each to have a good chance of being prime, so that the total probability sums to more than 1. And so what Goldstone, Pintz, and Theorem did was that to make each of these guys likely to be prime, they decided to take all these linear factors and multiply them all together to get this big polynomial, and try to force this polynomial to have very few prime factors, what's called an almost prime. Because if this number has very few prime factors, then that increases the chance that each of these guys will be prime. And there's a standard way of doing that, and it's called the Solberg sieve. There's a probability density which will enhance the probability that this has few prime factors. Okay, and it's given by a certain formula, but maybe I'll not talk about the formula exactly. But so they chose a sieve. There's a parameter in it called f, and you optimize in f. There's a calculus of variations problem you have to solve, and then this gives you the result. Okay. All right, and you have to use a bunch of number theory, not just the prime number theorem. You have to use a more advanced form of the prime number theorem called the Bombrier-Vinogradov theorem, which counts not just primes in an interval, but primes in arithmetic progressions. And what Yitang Zhang did, his big breakthrough was that he didn't improve the sieve theory part. Well, he made some improvement to the sieve theory part, but his principal improvement was he improved this Bombrier-Vinogradov theorem, that he found a more refined estimate for how many primes there are in certain arithmetic progressions that went beyond what people knew before. And this was quite a difficult piece of work. Just to give you one example of what goes into it, it used Pierre Deligne's proof of the Riemann hypothesis over finite fields, which is what gave him both the Fields Medal and the Abel Prize. And that's an essential ingredient in Zhang's work. But because he improved this part of the argument, he was actually able to get a bounded gap, which we later improved to about 4,000. Okay, but what Maynard did, and actually I came up with the same idea at the same time, actually by coincidence, was that Maynard instead improved the sieve theory part of the argument, and then bypassed the need to use all this fancy work of Deligne. As I said before, what Goldstone, Pintz, and Theorem did was that they chose this probability distribution by multiplying all your linear factors together to form this polynomial, and then tested the divisors of this polynomial to create this sieve. You want to remove all those values where this polynomial is even or divisible by 3, and so forth. Maynard's idea was that rather than do this sieve, which is what's called a one-dimensional sieve, you do a multi-dimensional sieve. So rather than put all your factors together into one big number and then try to study that big number as in aggregate, you look at each of the numbers separately and you factor each of the numbers separately, and you run a sieve based on the factors of each of the d separate numbers. So you have this multi-dimensional sieve which you couple together by a certain cutoff function, which is based on the sizes of all the factors of all these numbers. So it's a more complicated sieve, but the point is that the original sieve had a parameter which was this one-dimensional function, and this new sieve has a parameter which is a multi-dimensional function. And then you have to optimize this sieve, and you have to now solve this calculus of variations problem involving a multi-dimensional function, which looked really complicated, and it is really complicated, and no one really attempted to optimize this before because it just looked too scary. But actually, James actually found a way to get a good choice of f that actually worked quite well in this multi-dimensional variational problem, and this is how you can get these really good prime gaps, which currently is 246. Okay, so that's small prime gaps, and that's actually all I want to say about small prime gaps. So I want to talk about the more recent developments from last year on large prime gaps. Okay, no, maybe no, hang on. Before I do that, I have to mention one thing. Sorry. So this argument of Maynard, actually, it's so efficient. So as I said before, the moment you can get these probabilities that this is prime, this is prime, this is prime, the moment you have them add up to more than one, then the pigeonhole principle tells you that you can get two primes, that two of these guys are going to be prime at some point. But actually, Maynard's argument is so efficient that not only can you get these probabilities to be bigger than 1, but if you make k big enough, you can make these probabilities sum to be bigger than 2, or bigger than 3, bigger than 4. And so as a consequence of his work, not only can you get 2 of these numbers to be prime, you can actually get 3 of them, or 4 of them, or 5 of them to be prime if you want. So not only can we now bound prime gaps, but we can actually bound sums of consecutive prime gaps. So we can take 2 prime gaps and put them together, like Pn plus 2 minus Pn, and we can make those guys bounded as well. So I mention this because this will be important for the large prime gap theory. Okay. So now back to large gaps. Okay, so all right, so now we're looking at the opposite problem. We pick a large number x, and this time we'll take all the prime gaps from 1 to x. And now we look at the largest prime gap, we'll call it g of x. Take all the gaps that you can find from 1 to, say, 1 trillion. What is the largest gap that you can find? So this should get bigger as x gets bigger because there's more and more prime gaps, but how does it grow? Okay, so you can again use the pigeonhole principle. And if you run the pigeonhole principle just the other way, you can show that the average gap is log x. So somewhere in this in your interval, you must have a prime gap bigger than log x. So the prime gaps do grow, and they must grow by at least log x. Now, that's the lower bound. How fast can they grow? Well, I mean, they can't be incredibly huge. So for example, they must be less than x trivially. Okay. But you can do better than x. In 1920, Kramer showed that if you assume the Riemann hypothesis again, which is a very useful hypothesis in number theory, you can get basically root x. You can get up front of root x. And in 36, he made a very influential probabilistic model for the primes called the Kramer random model, which predicted he predicted but not actually proved that the gap should actually grow like log squared x, because that's what the gap would be if the primes were just a completely random set with that density. So log squared x is what we believe to be the answer. Actually, there's a slight tweak. We actually believe it to be, nowadays we actually believe it to be about 20% larger than log x. But there's a slight defect in this model that you have to tweak. But we believe that the true gap should be about log squared x. Okay, so we can get a lower bound of log x, and on the Riemann hypothesis, we can get upper bound of about root x. Without the Riemann hypothesis, it's harder, but you can get close to root x. The best bound we know currently for without the Riemann hypothesis, on the best upper bound on the large gap is x to the 0.525. So basically root x. So there's a huge gap between the upper bound and what we think is the truth, which is log squared x, but there's not that much of a gap between the lower bound, which is the trivial lower bound log x, and what we believe to be the truth of log squared x. So you'd think that this is not such a big gap. Log x and log squared x doesn't look that far apart. But it was quite a journey to, well, we haven't got it yet. But can you improve upon this log x? So we saw for small gaps that there was this long period of slight improvement until we got this big breakthrough. And there's a sort of similar story for large gaps. So as I said, you can get a gap of 1 times log x. Okay, and so again, people started improving the constant. In 29, Becklin got 2 times log x, 4 times log x. And then with Cynthius, I showed that you can actually get log x times something that grew a little bit. Not very fast, a log x over log x, which does grow to infinity, but not very quickly. And then Erdős came and improved the logs a little bit. Now it's log x over log x squared. And then Rankin improved Erdős by a log x. And so, so he showed that you can get a prime gap from 1 to x of size log x times log x, log x over log x squared. There's this joke, what did the drowning number theorist say? Is it log. Okay. Yeah, we like our logs. Okay, so these are all kind of random. So we try to get log squared x. And this is 1938. Okay, so that was like 70 years ago, 75, 70 odd years ago. So you think that we should still, we should be able to improve this. But for the next 70 years, the only activity that happened was with this c. As I said, g of x is bigger than a constant c times this whole mess of logs. And the only thing that happened for 60 years was that you can improve the c a little bit. So Rankin actually got c as a third, and then the c is slowly increasing. But we couldn't budge these logs. This is not what should be the truth, right? So the truth is log squared x. But we had all this funny mess of logs, which no one could shift. You could only improve the constant a little bit. And so it got so frustrating that Erdős, who was quite fond of giving cash prizes for problems, offered quite a big cash prize actually for anyone who could get off of this weird factor. So in '79 he offered this prize, which is actually the biggest prize he ever offered actually. For anyone who could show that this constant could be made arbitrarily large, or equivalently that you could attach some extra factor, maybe 10 more logs or something, on this end. Could you actually get off of this weird factor? And that was finally done. Kevin Ford, Ben Green, Sergei Konyagin, and I, in 20th of August last year, finally figured out a way to do this. Just by an amazing coincidence, the next day, completely independently, James Maynard found a different way to do it too. I think sometimes the time's just ripe for progress. Even though 70 years there was basically nothing, and then there was these 2 separate breakthroughs. Okay. In fact, and then we joined forces. So the 5 of us actually figured out exactly how much we could improve Rankin's bound. So Rankin's bound was log x, log x, log x over log x squared. And then what we could actually do, if we optimize everything in our methods, is that we can get rid of the square. So we can improve 1 log x. So it wasn't that spectacular of a gain, but it was some gain. Okay, still we're quite far from log squared x, which is what we really want. And unfortunately, none of our methods will actually get log squared x. This appears actually to be the limit of all of our methods currently. And so I think we'll be stuck here for quite a long time. So I decided to, in the spirit of Erdős's prize, to actually offer $10,000 to anyone who can improve on this. Not just on the C, but actually to actually to replace this by something that goes faster. But this seems to be the limit of what we can do now. Okay. All right. So how do we actually find large gaps? They all use the same idea, just sort of executed more and more efficiently. To find a large prime gap is the same thing as finding a big long string of composite numbers. If you can find a big long string of composite numbers, then the 2 primes on the end on either side of a string will be a large prime gap. So really, you want to find a big long string of numbers where everybody's composite. So the easiest way to do this, and sometimes you even see this taught in high school, is just to take a factorial, n factorial, and shift it by the numbers 2, 3, 4, up to n. So take a large number n factorial plus 2, n factorial plus 3, up to n factorial plus n. And this would be a long string of composite numbers because n squared plus 2 is divisible by 2, n squared plus 3 is divisible by 3. So n factorial plus 3 is divisible by 3, and so forth. So you have this big long string of composite numbers. And you can work out what this tells you for the largest prime gap. You plug in Stirling's formula, which tells you how big n factorial is. And what you find is that this simple argument gives you a lower bound, which is pretty lousy. It gives you log x over log x, which is worse than the Pintz principle argument, which is log x. But just because an argument is worse doesn't mean that it's useless. It means that it should be improved. So you can be smarter than n factorial. So if you don't use the factorial, you use something smaller called the primorial. So the factorial of a number is the product of all the numbers up to n. The primorial of a number n is the product of all the primes up to n. That's a smaller number. And actually, it turns out that you can just replace n factorial by n primorial. If you take n primorial plus 2, n primorial plus 3, up to n primorial plus n, those are still a string of composite numbers. Because every number between 2 to n is divisible by some prime less than n. And that prime also divides the primorial. So you will still get a big long string of composite numbers. And if you work out what that gives you with the prime number theorem, that will give you that you recover at least the trivial bound. So you get back the log x bound that the Pintz argument gives you. Okay. So then basically you have to do better than this. So can you do any better than what I just told you? So the key thing that made that previous construction work was that if you took all the numbers from 2 to n, all of them were divisible by a small prime. That each of the numbers from 2 to n was divisible by some prime less than n. That's what made the previous argument work. Another way of saying that is that if you take the residue classes 0 mod 2, 0 mod 3, 0 mod 5, you take the residue classes 0 mod p for all the primes up to n, those residue classes, those sets of integers, they cover this big interval. So you can cover the interval from 2 to n by all these residue classes. That's just a fancy way of saying that every number up to n is divisible by a prime up to n. And it's this covering property which is what's important. More generally, whenever you can cover any interval, let's say the interval from 1 to y, if you can cover any interval by residue classes, if you pick one residue class mod 2, one residue class mod 3, one residue class mod 5, and it doesn't have to be 0. You can pick any residue class mod 2, mod 3, mod 5. If you can find residue classes, you take all the primes up to some x. And if you can make these residue classes, if you can shift them in such a way that they cover this entire interval 1 to y, then a very similar argument to what I had on the previous slide, you need one extra trick, which is the Chinese remainder theorem. If you can cover this interval by residue classes, then you can slide this interval somewhere so that you can make them all composite. You just slide this interval until it's covered by the 0 mod p classes. And this will give you some lower bound on the largest prime gap. So basically, for example, if you want to prove Rankin's result, this funny log, the thing with all the logs in it, what you need to do is that you need to be able to cover the interval from 1 to y by residue classes mod primes up to x, and y just has to be a little bit bigger than x. Okay, so to get Rankin's result, y has to be x log x log x over log x squared. And then to get other results, you need other funny factors in front of this. But y has just a little bit bigger than x. So with this idea, you have transformed the problem from sort of a number theory problem to more of a covering problem. You have this interval, and you want to cover it as efficiently as you can using as few residue classes as possible. So the way I like to think of it is like shooting ducks at a fair. So this interval from 1 to y, you can think of as a big row of ducks. Okay, and what you have is that you have all these rifles. Okay, you have a mod 2 rifle and a mod 3 rifle and a mod 5 rifle and so forth. This analogy is a little bit forced, but bear with me. Okay, so what the mod 2 rifle does for you is that it shoots out one residue class mod 2. So you can shoot all the even ducks or all the odd ducks. Okay, but you can only shoot it once. Okay, and then you have the mod 3 rifle, which can shoot out one of the residue classes mod 3, 0 mod 3, 1 mod 3, 2 mod 3, but you can only shoot it once, and so forth. And so you have one rifle for every prime up to x. And your job is to aim these rifles in such a way that you can shoot all the ducks with the ammunition that you have. Okay, so that's sort of the way I like to think about the problem. I find that in working math problems, it helps to so anthropomorphize the enemy somehow. Essentially, something that you can shoot at in particular. Okay, but okay. Well, at least makes it more fun to think about. Okay. Okay. So it's so now basically the whole game is to find sort of efficient shooting strategies that sort of cover as you want to cover as many of these ducks as you can. So there's a lot of tricks, and you put all the tricks together, and this is what gives you the best results. So the first thing is that you don't actually need to shoot all the ducks. If you can shoot most of the ducks using most of your ammunition, then you can finish the job, because each one of your residue classes can always remove at least one of your survivors. If you have one duck left over and you have one residue class P that you can choose, you just pick the P whose residue class hits that duck. So basically, for example, if instead of using all the primes from 1 to x, you use all the primes from 1 to x over 2, and you shoot many of the ducks and there's some survivors, if the number of surviving ducks is fewer than the number of remaining primes, then you just use each of the remaining primes to eliminate one duck, and then you can solve everything. So basically, you don't need to cover 100% of your space. You just need to cover 99% basically, and that's a much easier problem mathematically. Once you allow yourself to this error tolerance. Okay, so that's the first observation. The second observation is that that you already have this pretty good strategy, which already removes a lot of ducks, which is you just keep shooting 0 all the time. Okay, so if you shoot 0 mod 2, 0 mod 3, 0 mod 5, this is the Sieve Eratosthenes. This already removes most numbers from your set. It doesn't remove everybody, but it removes a fair number. So like if you shoot out 0 mod p for every p up to say x over 4, then you eliminate every number which is divisible by a prime up to x over 4, and the only numbers that are left, well, first of all, 1, because 1 isn't divisible by anything. 1 is left, and all the primes between x over 4 and y. So basically, the Sieve Eratosthenes shoots out everybody except the primes. Unfortunately, there's too many primes, so this by itself doesn't solve the problem. But so what you want to do is you want to modify the Sieve Eratosthenes to be a bit more efficient than this. Okay, so all right. So then the next observation is that there's a little bit of inefficiency in the Sieve Eratosthenes. You don't actually need, so the Sieve Eratosthenes sieves out 0 mod p for every single p up to some threshold, x over 4. But actually, most of those p's are not needed, because if a number is divisible by one prime, it's usually divisible by another prime as well. And so there's a lot of redundancy. So you can save, you can keep some of your, you can reserve some of your ammunition, if you like, for doing something else. So rather than remove 0 mod p for all p, if you remove 0 mod p for all p, okay, if you remove all small primes less than y over x, okay, and all large primes between some threshold z and x over 4, but you don't remove 0 mod p for medium primes. So if you take out some medium interval of primes between y over x and some z, and you don't remove those, and you only remove 0 mod p's for all the remaining primes p, that's still a pretty good sieve. That's still so if you do that sieve, you will still keep 1, and you'll keep all the numbers that are prime, but you'll get some extra. You'll get some extra numbers now because which were not removed. Because if you don't shoot out the primes less than z, then you will keep some new numbers, and you'll keep the numbers which are called z smooth. So a z smooth number is a number where all the prime factors are less than z. So these are all the numbers which would survive if you are not shooting out multiples of primes less than z. So if you remove these, if you remove these residue classes from the Sieve Eratosthenes, you get some additional numbers, these z-smooth numbers. But if z is small enough, then the number of these z-smooth numbers is pretty small. So number theorists have worked out exactly how many smooth numbers there are up to x, which are z-smooth, and there's a formula which is moderately complicated, and you can optimize the formula. And it turns out that the biggest you can hope to make z and still not take on too many extra numbers is this funny power of x. It's if you make z be x to the log x over log x. That's how many sort of mod p's you can remove and still not increase too much the number of primes, number of survivors that you have. And it's this funny exponent. This is what leads to all the weird exponents in the Rankin band and so forth. It's because of this guy. Okay, so you take out some of the residue classes from the Sieve Eratosthenes, and so what do you do with them? Well, the best thing we know how to do with these residue classes that we saved, is just to shoot randomly. Which is so for all the primes between y over z and y of x and z, you just pick a residue class at random, and that cuts down the number of surviving ducks by a certain factor, which you can compute. And when you work it all out, this is basically Rankin's method, and this is what gets you this weird Rankin bound of Rankin with all the logs in it. Okay, so that's Rankin's method, and it uses all the primes up to about x over 4 and between x over 2 and x, and you just have one sort of round of ammunition left, which is all the primes between x over 4 and x over 2. And so so all the remaining advances past the 1938 result of Rankin was just how to use these large primes, how to shoot using these large primes p as efficiently as possible. And so what Rankin did was that he just used each of these large primes to shoot one duck. Okay, and that's how he got his original bound. And over the next 60, 70 years, the constant c that got improved basically came from the idea that maybe you can use these primes to shoot 2 ducks at a time rather than 1. And so that's basically how the constant slowly got improved, but it was not a very great improvement. But if you want to do better than that, so I mean the obvious thing to do once you see that is you want to find residue classes A mod p, where p is pretty large now, so very sparse arithmetic progressions, which are not just capturing one duck or 2 ducks, so not just capturing 1 or 2 primes, but they're capturing many primes. So you want to find an arithmetic progression of large spacing, which captures many primes, 3 or 4 or 5 primes at a time. We now know of 2 ways to do this. So Kevin Ford and Sergei Konyagin were working on this problem, and they realized that what they needed, one thing that would solve the problem was that if you could find arithmetic progressions that consisted entirely of primes, that's like a residue class that contains lots of primes. And by coincidence, Ben Green and myself had actually worked on this problem many years ago. We actually had a method for finding progressions with lots of primes in them, and so that's how we got involved in this project. So in 2004, Ben and I were able to find lots and lots of arithmetic progressions of any length you wished, where every number was prime. This wasn't quite what Kevin and Sergei needed, because not only did they need the entries of the progression to be prime, they needed the spacing r to basically also be a prime as well. So we had to modify our arguments, but it turns out this is possible with a bit of work. To also make R, actually not quite a prime, but a multiple of a big prime. And this turns out to be enough to improve Rankin's result, and you can make the C arbitrarily big. So that's how we did it. And then the next day, James Maynard had a different argument, where instead of using what Ben and I did on progressions and primes, we used what James did in his work on small gaps. So as I said before, one spin-off of what James did in his work on small gaps was that he could find many n for which, so given any h1 and hk, he could, for k big enough, you could find many n for which n plus h1 and n plus hk contained many, many primes. Let's say 10 of these guys are prime at a time. So he could find many tuples where many of these numbers are prime. And it turns out that there's a very similar argument where you take all these shifts and you multiply them by a large prime p. And for any large prime p, you can also find lots of n for which n plus h1 times p, n plus h2 times p, just this dilated shifted tuple. You can make sure that this set has got lots and lots of primes in it, let's say 10 primes in this set. So that would imply that a certain residue class mod p contains lots and lots of primes. And so that so by using that, actually, that gives you a different way to make this bound large. Actually, his way is actually better than ours. It gives a better bound, actually, if you work through the computation. Okay, so this that almost so that solves the original problem of Erdős of getting the constant arbitrarily large. The final thing we did was to optimize everything and get rid of this square. And so we have this final bound where we only have log x rather than log x squared. The previous arguments that I just said don't quite give you this bound. They're off by a log x. Okay, they're off by a tiny amount. The reason is because sort of a lot of the residue classes that we were removing, they're sort of they're not coordinated with each other. So we're sort of shooting a whole bunch of ducks and we're shooting a whole bunch of other ducks. But many of these ducks get shot twice. Okay, we waste some of our ammunition by removing primes that were already removed by a previous stage of the sieve. And so we do that because it's easier to analyze if you just shoot randomly. It's much easier to compute how many survivors there are. But what you would like to do is to do things much more efficiently and to choose your aim somehow so that there's not much overlap, not much waste. And this turns out to be a special case of a problem that combinatorialists have studied for quite a while, which is something called a hypergraph covering problem, where so a hypergraph, so a graph is a bunch of edges, right? And edges are pairs of vertices. So a graph is a collection of sets of sets of vertices of size 2. A hypergraph is a collection of sets of vertices where the number of vertices, the number of elements in a set can be more than 2, like 3 or 4 or 5 and so forth. This is called a hypergraph. Harder to draw than a graph, but sort of generally the same. And in our case, the vertices are the primes, and the hypergraph consists of like residue classes intersecting the primes in various ways. Okay. And what we have is this covering problem. Given this hypergraph, this collection of subsets, what is the most efficient way to cover your whole set or most of your set by these subsets so that there's as little overlap as possible and you get as much coverage as possible. So that's a general combinatorial problem. So if you do it randomly, there's some overlap, there's a bit of waste. But there are smarter ways than random to do this. And so back in '89, there was developed something which we now call the semirandom method, or the roto nibble, developed in particular by Pipitner and Spencer. And so the idea is that if you're going back to the shooting analogy, so rather than just sort of shoot randomly and get all this overlap, you shoot randomly for a small amount of time. So you take a small amount of primes and you shoot randomly, but only for a small set of primes. And as long as you only take a small set, there's not much overlap. Like the overlap only comes when you shoot a lot. So you shoot a little bit at random, and then you remove all the ducks that got hit by that process. And then for the next set of, so that's one nibble. Then for the next nibble, the next set of primes, you choose randomly among all residue classes that don't hit any of the ducks that were removed already. So you, rather than just pick your residue classes at random, you pick only those residue classes which avoid the elements that already got hit. You do that randomly for a while. Then you remove some new ducks, and then you take another nibble where you only you only shoot among all the residue classes that avoid everything that has already been removed. So this intuitively is a better strategy. The hard part is to analyze it and to actually make sure that it actually still works. But this actually can be done after a lot of effort, and it gives somehow the maximally efficient way to run all of these arguments, and that's what gives us this final bound. And that's where we're at. And as I said, that seems to be the complete limit of our methods. And I'm offering $10,000 to anyone who can do better than that. Okay, thank you very much.